Hi, we have already discussed your capacitors and resistors in the previous lesson. In this lesson, we are going to combine your resistors and capacitors into one circuit. And this is your RC circuit. We're going to discuss here your RC circuit and the charging and discharging process of your capacitor. So what is an RC circuit? An RC circuit, also known as an RC filter or RC network, stands for resistor capacitor circuit. An RC circuit is defined as an electrical circuit composed of the passive circuit components of a resistor, which is your R, and capacitor, your C, driven by a voltage source or current source. To the right is an example of an RC circuit. So this is a charging process of your capacitor in the network. And in the simple act of charging or discharging a capacitor, we find a situation in which the current, voltages, and powers do change with time. RC circuits include batteries or your voltage sources, resistors, capacitors, and switches. RC circuits will involve timing considerations. You have your time to fill up a capacitor with a charge, which is also called the charging of your capacitor, and the time to drain a capacitor that is already charged or your discharging. Now let's talk about charging your capacitor. We begin with the capacitor initially uncharged, as in the figure. So to the right is a simple RC circuit composed of your your voltage source, a resistor, and then a capacitor, and then you have an open switch. Take note again that this capacitor is initially uncharged. So again, we begin with the capacitor initially uncharged, and at some time, at some initial time equals 0, we close the switch. Okay, so we close the switch. So the circuit will now be like this, completing the circuit and permitting current around the loop to begin charging the process. So when the switch is closed, the charge on the capacitor increases over time while the current decreases. Because the capacitor is initially uncharged, the potential difference VBC, which is the potential difference across these 2 points here, or the potential difference across your capacitor, is 0 at time equals 0. So again, the moment you close the switch at time equals 0, the voltage VBC here in your capacitor is 0 because the capacitor is initially charged. If you remember, you have Q is equal to CV. Now, since you have your Q is equal to 0, then that means the voltage here is equal to 0. And at this time, at time equals 0, the Kirchhoff's, or from Kirchhoff's loop rule, the voltage VAB, or the voltage between these 2 points here, which is the voltage across the resistor R, is equal to the battery EMF. Consider if you're going to have this kind of travel here, counterclockwise, then you have from your Kirchhoff's loop rule, you have epsilon minus R IR that's equal to 0, or your epsilon that's equal to IR. And remember that your IR is just the voltage across your resistor, which is equal to the battery EMF. The initial current through the resistor, or the current at time equals 0, which we will call here as your I naught, is just given by your Ohm's law, where your I naught is equal to VAB over R. And since VAB over R is just equal to epsilon, then your I naught, or your current, your initial current through the resistor at time equals 0 is just equal to epsilon over R. This is again the initial current running through your circuit here as you close the switch. Now, as the capacitor charges, its voltage, VBC, or the voltage across here, increases. Again, as the capacitor charges, its voltage VBC increases, and the potential difference across the resistor decreases. So, as time goes by, the voltage here increases while the potential difference, or the voltage across your resistor, decreases, corresponding to a decrease in current. The sum of these two voltages is equal, or is constant and equal to epsilon. So in this closed circuit here, we will have a constant voltage which is equal to epsilon, But as time goes by, you have a decreasing current, signifying that you have a decrease of potential difference across your resistor and an increase of voltage in your capacitor. So again, when a switch is closed, the charge in the capacitor increases over time while the current across your circuit decreases. So let's review for a while. At time equals 0, so again at time equals 0, there is no charge in your capacitor. So in that case, your capacitor actually acts like a short circuit. So it's just like a wire here. So your capacitor acts like a short circuit. So it's just like there's no capacitor here and you only have a wire in this area here. So you just have your battery and then your resistor. So that is the case at time equals 0. And keep on charging. So as time goes by, the current in your capacitor decreases, or sorry, the current in your circuit decreases, signifying a decrease in voltage in your resistor and increase in voltage in your capacitor. And after a very long time, or after a long time, the capacitor becomes fully charged and the current finally decreases to 0. So as you have said earlier, as you charge your capacitor, the current in your circuit decreases. And after a long time, the current decreases to 0 and the potential difference VAB across the resistor then becomes 0. The entire battery EMF then appears across the capacitor and your VBC, or the voltage across your capacitor, is now equal to your epsilon. So what happens here is that after a very long time, so let's say at time is equal to, or as time approaches infinity, okay, your capacitor here becomes an, or your circuit here becomes an open circuit, only having your capacitor. And that is because when your capacitor is already filled, it does not anymore allow for more charges to flow. So it becomes an open circuit. And therefore, the voltage across your capacitor here appears to be equal to epsilon. We can actually derive expressions for your varying charge Q and varying I. Here we let Q to represent the charge on the capacitor and I to represent the current in the circuit at some time t after the switch has been closed. We chose the positive direction for the current to correspond to positive charge flowing onto the left-hand capacitor plate. As you can see here, the direction of your current has been chosen so that your current I flows from plus Q to negative Q. Take note here that we are using small letters Q and I because you have here your time varying Q and I. If you have instead big letter Q and or capital letter Q and capital letter I, that means those are constants in your circuit. That means those constants do not anymore change. The instantaneous potential difference VAB across your resistor and VBC across your capacitor are given by the following. You have VAB that's equal to IR and VBC that's equal to Q over C. VAB is time varying because you have a time varying I, and VBC is time varying because you have a time varying Q. Now using this in the Kirchhoff's loop rule, okay, here we apply your Kirchhoff's loop rule here. Let's say that you have your travel of a counterclockwise travel. Okay, and we apply your Kirchhoff's loop rule here. So we first have your epsilon, which is your EMF, minus the voltage in your IR. So you travel with the direction of the current. So you have minus IR. And then minus Q over C, the voltage in your capacitor. So it's minus again because you travel in the direction of your current. And you have this expression equal to 0. And the potential drops by an amount of IR as we travel from A to B, and by QC as we travel from B to C. So what we see here is that your EMF drops as you travel in IR and also as you travel with Q over C. And from this equation here, we can solve for I. Okay, solving for the small I here, you have your I that's equal to epsilon over R minus Q over RC. So again, you have this expression. So we solve for I. I is equal to epsilon over R minus Q over RC. And at time equals 0, when the switch is first closed, the capacitor is uncharged again here. So that means your Q is equal to 0. Again, only for the case of at time equals 0. And substituting Q that's equal to 0 above here in this equation, we find that this expression just blows out. So this is equal to 0, and then you just have your I that's equal to epsilon over R. And again, we are looking at at time equals 0 here. And we have stated earlier that at that time you have your initial current I naught, which is just given by your epsilon over R. So we have here the same expression that we have in the previous slides. You have your I naught that's equal to epsilon over R. So we are still playing with this equation here. So earlier we set your Q equals 0 at time equals 0 when your capacitor is initially uncharged. And as the charge Q increases, okay, again, as you have said earlier, as you're going to charge your capacitor, your current decreases, signifying a decrease in the potential difference in your resistor and an increase in the potential difference in your capacitor. And as the charge Q increases, the term Q over RC, this term here, becomes larger and larger, and the capacitor charge approaches its final value, which we call your QF. So you have your big Q here as saying as you have your constant Q, meaning the Q that doesn't change. So you have your Q final, the final charge. And again, as the charge Q increases here, the term Q over RC becomes larger and the capacitor charge approaches its final value, which we will call QF. The current decreases again here in your charging process and eventually becomes 0. And here, your potential difference across your resistor becomes 0. And since the current becomes 0 when I equal 0, this equation here, you have here, this is equal to 0. So you have 0 here. That's equal to epsilon over R minus Q over RC. And you have this equation now here. You have epsilon over R that's equal to QF over RC. So we replace your Q with a big QF because we now approach the final value when your current is equal to 0. And you can just eliminate R and you can solve for your Q. That's equal to your capacitance times epsilon naught. This is just the formula of finding the charge in your capacitor. And remember again that as time increases or as time goes by, this becomes an open circuit. Like you just have your capacitor here. Okay? And note that the final charge Q, as you can see here, does not depend on the value of R. So whatever your R is, your final QF does not depend on R. These are the graph of the current versus time for charging the capacitor. So this is I versus T. And this is the graph of the capacitor charge Q versus time for charging a capacitor. And as you can see here, at time equals 0, which is at this point here, the current jumps to I naught, the maximum current or the initial current in your RC circuit. And the current decreases exponentially with time as the capacitor changes. And this is the graph of your Q versus your time. And as you can see here, it starts with 0 at time equals 0. And the charge on the capacitor increases exponentially with time toward the final value UF. We can actually derive general expressions for the charge Q and current I as a function of time, with our choice of the positive direction of the current, here as your current flowing in this way. Your I equals the rate at which positive charge arrives at the left hand, the positive plate of the capacitor. So your I is equal to dq over dt. Making this substitution, you have your I that's equal to epsilon over R minus Q over RC. So we have this equation here earlier, and we substitute this one. to this equation, we have dq over dt that's equal to epsilon over r minus q over rc. Okay, and we can actually take out rc of the equation. Okay, so we just take out negative 1 over rc out of the equation. So you have negative 1 over rc times q minus c over epsilon. Or you can just take out rc and then you interchange your q and then your epsilon, whatever way you like. That is just this equation here. We substitute dq over dt. So you have dq over dt that's equal to negative 1 over rc times c minus c times q minus c epsilon. So we have this equation. You have again your dq over dt that's equal to negative 1 over rc times q minus c over epsilon. And just by this one, we can rearrange this one to this form. So we arrange again this one into this form. So you have dq over q minus c times epsilon. So we just divided both sides of the equation by q minus c epsilon, and then we multiply by dt. So we rearrange our equation into dq over q minus c times epsilon that's equal to negative dt over rc. And you can solve this one by integrating both sides. But before integrating, we change the integration values to q prime and t prime. So this one here, we change this one into dq prime and then this one into dt prime so that we can use your q and t for the upper limits and the lower limits are q prime is equal to 0 and t prime is equal to 0. That is here. You have these equations integrating. Your lower limit is from 0 to q. That is when the charge is equal to 0. And then when your charge is equal to q. And then on the other side, you integrate from at time equals 0 to at any time t. So we can now solve this one, integrating both sides. So we have again this expression here. And again, what we're going to do is to integrate this one. In integrating the left-hand side, as you can see, this is equal to some ln times a function. And then integrating the right-hand side, you have your t over rc. And as you can see, as there is an ln here, the natural logarithm, we exponentiate both sides. That is, we multiply by t. Okay, exponentiating both sides, that is taking the inverse logarithm and solving for q, we find that you have your q minus c epsilon over negative c times epsilon, and then that's equal to e times negative t over rc. And rearranging to solve for q, this expression here, this will become your q that's equal to c times epsilon. So we just took out the c times epsilon out of the equation. So c times epsilon times 1 minus e times negative t over rc. Or as you can see, this is a big c and then your epsilon. This is just again equal to your charge qf. So we can replace this one by qf. So your q is equal to qf times 1 minus epsilon to epsilon negative t over rc. And this is the function for your charge q as you charge your capacitor. And you see here, you have your epsilon, which you'll see later in the graph. And then the instantaneous current I is just the time derivative of the equation above. So you can take the time derivative of this one. That is, you have your dq over dt. Okay, so that's equal to the current I. So you also take the time derivative of this one. So you have the instantaneous current I is just the time derivative of the equation above. That's equal to I. It's equal to epsilon over r times e negative t over rc. And as you can see here, your epsilon over r is just your current I naught, your big I naught. So your I is equal to I naught e times negative t over rc. This is again the current for your charging of your capacitor. So we have now the equations for your changing Q and then your changing I, or your instantaneous Q and then your instantaneous I. And this is what your equations represent. So you have your I here that's equal to I naught. So as you can see, at time equals 0, if this is 0 here, it jumps to I naught. So you have only I naught here. And as time increases or as time goes by, the current decreases exponentially here because you have this exponential expression here. So this is the decrease in your current I until it approaches to 0. And this is the graph for your, again, for the your capacitor charge versus time for charging a capacitor. So at the beginning, if this is 0 here, so you have your 1 minus 1 is 0, so your Q is 0. And the charge on the capacitor increases exponentially because you have this exponential expression on this side here. And if this is very big, so you have negative E up to very big time t, then this goes to 0, and then so you only have your QF times 1. One application of your RC circuit can be seen in pacemakers. So pacemaker is used when your heart is not working well. So this is here an X-ray image which shows a pacemaker implanted in a patient with a malfunctioning sinoatrial node, the part of the heart that generates the electrical signal to trigger your heartbeat. So that you have your heartbeat going well, you need to uh, you need the help of a pacemaker. And your pacemaker circuit contains a battery, a capacitor, and a computer control switch. To maintain regular heart beating once per second, the switch discharges the capacitor and sends electrical pulse along the lead to the heart. The switch then flips to allow the capacitor to recharge for the next pulse. So you have discharge and then discharging, or you have a charge and then you're discharging again, then you charge it again, and then you discharge again to mimic your heart beating or to mimic the electrical signal to trigger your heartbeat. You have actually seen earlier in the equation for your charge Q and then for your I in your RC circuit, your charging process, that you have the specific product of your resistor and then your capacitor. So in charging the circuits, the time constant tau is actually equal to your RC. And your tau is a measure of how quickly the capacitor charges. So in one time constant, for example, the current drops to 1 over E, okay, here, or the current drops to 1 over E of initial value, about 36%. In the charge in the capacitor plates rises to around 64% of the maximum value. So you have your time constant tau that measures how quickly the capacitor charges, and that's just equal to your R times C. Your tau increases with R, larger resistors decrease your current, and less charge per time arrives at the capacitor. And if you have larger R, it takes a longer time to fill up your capacitor. Your tau also increases with your capacitance. Larger capacitors have more capacity, thus they take longer time to fill up. Now suppose that the capacitor in the previous charging process of the circuit here has acquired a charge Q. So you have now your big Q. So that means here that your capacitor is fully charged. And suppose you remove the battery in this circuit and connect points A and C into an open switch. That is, you have this one here. So you have again this circuit where we remove your battery and your capacitor has a charge Q. So your capacitor is fully charged. We then close the switch and at the same instant we reset our stopwatch to time equals 0. So we start again with time equals 0. If the switch is closed, the capacitor discharges through the resistor, and its charge eventually decreases to 0. So this is how you're going to discharge a capacitor. Connect it with a resistor, and then you close the circuit, just like this one here. And your capacitor, the charges in your capacitor discharges into your resistor. And you'll observe that your resistor actually becomes hotter as time goes by. So when the switch is closed, the capacitor or the charge in the capacitor and the current both decreases over time. Again, let's say that you have your I and Q represent the time varying current and charge at some instant after the connection is made. We make the same choice of the positive direction for the current like before. So we have this one here. Then from Kirchhoff's loop rule, you have applying Kirchhoff's loop rule here. You have negative IR minus Q over C that's equal to 0. Solving for I, which is dQ over dt, your I is equal to negative Q over RC. So you just solve your I from here, and your I is equal to negative Q over RC. And as you can see, you have a negative I. The current I is now negative. This is because your positive charge Q is leaving the left-hand capacitor plate, so that the current is in the direction opposite to that shown in the figure. That is, the current should be supposedly going to the left or traveling clockwise. So you have your I that's equal to dq over dt, or that's equal to negative q over rc. And at time equals 0, when your Q is equal to Q naught, or when your capacitor is still fully charged, the initial current is equal to I naught, that's equal to negative Q naught over RC. So this is when you have this is when the moment you close the switch. So you still have your maximum I naught and then your maximum Q naught. So we go back here with this equation, and to find Q as a function of time, we arrange above. So we just have this one here. You have dq over dt that's equal to negative q over rc. And rearranging, so you have dq over q and then dt over rc. And then integrating, you also change your variables from q to q prime and t to t prime, so that we can use your q and t as your upper limits. So to find q as a function of time, we arrange above and integrate. Integrating, you have ln q over q naught, and this is equal to negative t over rc. So you see here that the integral of this one is ln q, and then you have here t. So you have negative t over rc. And solving for q by exponentiating both sides, so you multiply this one by e, and then also multiply this side here with e. Your q is equal to q naught epsilon negative, or q naught e negative t over rc. And this is your q for your for charging your capacitor. And then your I, which is equal to dq over dt, that's equal to negative q naught over rc e negative t over rc, or since your q naught over rc is just equal to your uh, your 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 current I naught, so you have your I is equal to I naught e times negative t over rc. These are the equations q and I naught, your time varying q and then your time varying I for your RC circuit when you are discharging your capacitor. So these are the graph of the current versus time for a discharging capacitor. As you can see here, at time equals 0, the current drops to I naught, and then the current decreases exponentially as the capacitor discharges. The current is negative because its direction is opposite to that of the previous discussion. Here is the equation. So you have exponential decrease because of this exponential term here. And On the other hand, you have here the graph of the capacitor charge versus time for discharging the capacitor. So at time equals 0, your Q naught jumps to, or your Q jumps to Q naught, the maximum charge, because at this point here, your capacitor is still fully charged. And the charge in the capacitor decreases exponentially as the capacitor discharges. This graph here can be represented by this equation. You have your Q is equal to Q naught E times negative T over RC. So it's exponentially decreasing because, again, of this exponential term here. Now let's have an example. This is for charging a capacitor. A 10 mega ohm resistor is connected in series with a 1 microfarad capacitor and a battery with EMF of 12 volts. Before the switch is closed at time equals 0, the capacitor is uncharged. What is the time constant? What fraction of the final charge QF is on the capacitor as time is equal to 46 seconds? And what fraction of the initial current I naught is still flowing at time 46 seconds? Again, you have a 10 mega ohms resistor that is connected in series with a 1 microfarad capacitor and a battery with EMF 12 volts. So you can just imagine the circuit that we have when discussing about charging your capacitor. Before the switch is closed at time equals 0, the capacitor is uncharged. What is the time constant? And what fraction of the final charge QF is on the capacitor at time equals 46 seconds? What fraction of the initial current I naught is still flowing at time equals 46 seconds? Solving for the time constant tau, so tau is just equal to RC. And you can change your variables into your SI units. So you have 10 times 10 to the 6 ohms times 1 times 10 to the negative 6 farads. So your time constant is equal to 10 seconds. That is, your capacitor will be charged just for 10 seconds. Okay, so that is 8. Next, what fraction of the final charge Q is on the capacitor at time equals 46 seconds? So we are asked the fraction Q over QF. So again, you're asked of the fraction of the final charge. So that means you have your Q over QF. So this is just your formula here. So we have 1 minus E to the negative P RC. So you have 1 minus E to the negative 46 seconds divided by 10 seconds. So you have 0.99. So that means at 46 seconds, your capacitor is almost fully charged. Next, what fraction of the initial current I naught is still flowing at 46 seconds? So your S of the fraction of the initial current I naught, that is your S of I over I naught. So we have this equation here. So this is just a direct solving. So you have your I over I naught is equal to E times negative T over RC. So you have E to negative 46 seconds divided by 10 seconds. And that is equal to 0.010. So that means there's only around 1% of the initial current I naught is flowing at 46 seconds. As you can see, the charge is equal to 0.99 or around 99%. So there's just a small fraction of time that is flowing in your RC circuit. Let's have another example. We use the same resistor and capacitor of the previous example that are connected as shown in the figure. So this time, the capacitor has an initial charge of 5 microcoulombs, and this is discharged by closing the switch at time equals 0. So at what time will the current be equal to 0.50 microcoulombs? And what is the current at this time? So we are asked of your discharging of your capacitor, and we're first asked of the charge or the time when the charge is equal to 0.50 microcoulombs. So that means your Q here, your small q is equal to 0.50 microcoulombs. The initial charge, your Q naught, is 5 microcoulombs. Okay. And we solve for the time just by playing with this equation. or taking or multiplying this one by ln both sides. Okay, so we have P that's equal to negative RC times ln Q over Q naught. Again, in order to take out your time T here, you multiply the equation by ln both sides. That is like this one. You have ln Q here and then ln of this one. Okay, so ln times E that's equal to 1, so you can take up can take out the E. So you have you can now solve 4 times. So you have your T that's equal to negative RC ln Q over Q naught. Your Q is equal to 0.50 microcoulombs, and then your Q naught is equal to 50 microcoulombs. And you know RC, that's equal to 10 seconds. Solving for this one, your time is equal to 23 seconds. So that means when the charge in your capacitor is equal to 0.50 microcoulombs, it already took 23 seconds from 5 microcoulombs. Next, what is the current at this time, meaning the current at 23 seconds? So we just use this equation here with Q naught equals 5 microcoulombs, which is equal to 5 times 10 to the negative 6 coulombs. So you have your I is equal to negative Q naught over RC. So we just change this I naught here with Q naught over RC times E negative T over RC. So you have 5 times 10 to the negative 6 coulombs divided by 10 seconds, then E to the negative 2.3. Okay. So this is equal to negative 5 times 10 to the negative 8 amperes. So at 23 seconds, you only have negative 5 times 10 to the negative 8 current that is flowing in your circuit. Negative because, again, your current actually flows in the opposite direction. Let's have another example. In the circuit shown, both capacitors are initially charged to 45 volts. So you have two capacitors that are in parallel, and both of these capacitors are initially charged to 45 volts. How long after closing the switch S will the potential across each capacitor be reduced to 10 volts? And what will be the current at that time? So as you can see here, this is actually a discharging process, and your two capacitors initially are charged at 45 volts, and you're asked to find for the time in which your capacitors will only have 10 volts each, and also what will be the current at that time. So again, first you're asked for how long after closing the switch S will the potential across each capacitor be reduced to 10 volts. So both capacitors are initially charged to 45 volts. And as you can see, the capacitors, which are in parallel, will discharge exponentially through the resistors that are in series. So you can actually just simplify this one with having one capacitor and then one equivalent resistor. Remember that your Q is equal to your CV, and we only have this expression here, which is your Q is equal to Q naught E to the negative T over RC. And from here, since your voltage is proportional to your Q, your voltage must obey the same exponential equation as Q. So we can derive an equation for the voltage of this form here. And again, since your V is proportional to Q, so they must obey the same exponential equation as Q. That is, we can just change this one with your V, small v, and then your V naught. So you have your V that's equal to V naught epsilon negative T over RC. Remember that you're given with the capacitor is initially charged to 45 volts, and then you're asked for the time when the charge is only at 10 volts. So we need an equation wherein you have your voltage in your equation. And this is this one here. Solving for the time when the potential across each capacitor is 10 volts, you have your V that's equal to V naught E to the negative T over RC. Solving for time by taking the natural logarithm or multiplying ln on both sides, you have negative RC times ln V over V naught. So your RC is just 80 ohms. So this is just in series times 35 microfarads, which is the equivalent capacitance of this one, of these two parallel capacitors, times ln 10 volts over 45 volts, which is equal to 42 or 4,210 microseconds, or is equal to 4.21 milliseconds. What will be the current at that time? So the current is just this one. You're discharging. I is equal to I naught T negative T over RC. And remember that your I naught is equal to V naught over R from your Ohm's law. So your I is equal to negative, or is equal to V naught over R E negative T over RC. Solving for time, or solve for the time in the potential across each, or sorry, solving now for your current I. So you just have your V naught over R E negative T over RC, that's equal to 45 volts divided by 80 ohms, times E to the negative 4,210 microseconds divided by this one here. So we can use your microseconds because you have your microfarads here, and this micro can just be cancelled by this micro here. Okay, so this is okay. Or you can convert this one into seconds, also this one into farads, you'll get the same answer. But we just use your microseconds here because we have your microfarads here, which can be cancelled out. And your current is equal to 0.125 amperes. We have a last example. In the circuit, the capacitors are initially uncharged. The battery has no internal resistance, and the ammeter is idealized. Find the reading of the ammeter just after the switch S is closed, and B, after the switch has been very close for a very long time. So you have this circuit here, and then we inserted some ammeter to measure the current. Again, the purpose of your ammeter is to measure your current. And we're asked of the reading in the ammeter after the switch S is closed, that is at time equals 0, and after the switch has been closed for a very long time, that is a time that approaches to infinity. So let's find first the reading of the ammeter just after the switch S is closed. And at time equals 0, just when the switch S is closed. Again, the potential across your uncharged capacitor is initially 0. So it behaves like a short circuit. So when we say this, it behaves just like a short circuit, that means there's just wire here, and then this is just a wire here, and then also here. These are just shorted. These are wires here. Just after closing the switch, the uncharged capacitors all behave like short circuits, so any resistor in parallel with them are eliminated from the circuit. So since this is already shorted, this one here cannot be read. Also this one here. This one here is eliminated. Also this one here. And your circuit just becomes like this. You have your 75 ohms, your 50 ohms, 25 ohms, and then 15 ohm resistors. And you still have your ammeter, and your 50 ohms and then your 25 ohms are in parallel. The equivalent resistance or equivalent resistor is just in series with your 75 and then your 15 ohms. We are asked of the current I. The equivalent resistance is 90 ohms, 75 plus 15 plus 16 ohms, which is this one here, the result of the parallel connection of your two resistors. And the equivalent resistance is equal to 106.7 ohms. We can now solve for the current I. Your current I is equal to 100 volts divided by 106.7 ohms, just from your Ohm's law. So you have 0.937 amperes. As you can see, we did not use any analysis that we have earlier. Just take note of the fact that for at time equals 0, the potential across the charged capacitor is initially 0 and it behaves like a short circuit. And then we simplified your circuit and we solved for your current I using your Ohm's law. Next, let's find the reading of the ammeter after the switch has been closed for a very long time. That is when your time approaches to your infinity. And a fully charged capacitor allows no current through it. So when we say that a fully charged capacitor allows no current to flow through it, long after this, after closing the switch, the capacitors are essentially charged up and behave like open circuits. So they become open circuits since no charge can flow through them. And if they become open circuits, they effectively eliminate any resistors in series with them. So here you have your three capacitors. So this one becomes open, that is, there is no connection anymore here. And then this one also becomes open, no connection there, and then also with this one here. So if that is the case, if these are open, they will effectively eliminate any resistors in series with them. And that's because since there's anymore, or since there's no current anymore that can flow through these resistors, and your circuit will just become like this. So if um, this is open, then you have a series connection here with your 25 ohms and then your 75 ohms. And you might say, some of you might say that why is 75 not eliminated? Take note here that uh, prior to that one, your 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 15 microfarad capacitor and then your 75 ohm resistor are actually not in series. So your 75 ohms is not eliminated. So this will just become open and then you have your 25 ohms, your 75 ohms. This one is removed because this has become an open circuit and nothing happens here. This is just removed. So we have your 25 ohms, your 25 ohms remains there, and then your 15 ohms also remains. So your circuit becomes like this. You have a series connection of your 25 ohms, 75 ohms, your 25, 25, and then your 15 ohms. So only one resistor has been eliminated, which is your 50 ohms. We can now solve for the current I. So your current I is just equal to 100 volts divided by 165 ohms, which is just the equivalent resistance of these 5 resistors here. And the current reading is equal to 0.606 amperes. Always remember here that what we just did was, after a very long time, your circuits become open because your capacitor allows no current to flow through it. So we just eliminated any resistor that is in series with your capacitor, and you can solve for the time. And remember that your ammeter is always connected in series with your circuit. That is how you're going to read your current in your circuit.